Hi guys, can you guys hear me?
Yes.
Okay. Right. So I'm going to continue where we left off from last week. So during last lecture, we have learned about the standard entropy. Okay, the standard entropy. S delta or the change in standard entropy, the delta S naught. Okay, S naught is the standard entropy. Change in standard entropy is delta S naught. And before we finish our lecture last week, we've learned how to calculate the standard entropy change of a system, of a reaction. Okay, when standard entropy values of products and reactants are given. Okay, so today we will continue on the entropy changes, but we will examine the entropy changes in the surroundings. Okay, so this was entropy system, entropy change, standard entropy change of the reaction of the system. Now we're going to look at the entropy change of the surroundings. Okay, so if you guys can recall, we learned this equation last week. Okay, we looked at entropy changes of the system. But in this slide, we will take a look at the entropy changes in the surroundings. Okay, so if heat, Q here is heat. If heat is produced or absorbed by a reaction or a system, of course there will be a change in entropy of the surroundings too, right? So what is the relationship? Their relationship is explained by this equation. Entropy change of the surrounding equals to the heat of the surrounding divided by constant temperature. Okay, but where do surroundings get their heat from? Heat. The heat that surrounding gets is from the reaction or from the system, right? So because whatever heat of the reaction or heat of the system produces, that amount of heat will be transferred to the surroundings. Or whatever heat reaction or system absorbs is, oh sorry, whatever heat the system absorb is transferred from the surroundings. Okay, so the heat between surrounding and heat of the system, they have negative relationship. Okay, so heat of the surrounding, when you're using heat of the surrounding, is going to be positive. When you're talking about the heat of the system, it's negative. They have negative relationship. Okay, and from Gen Chem 1, we already learned that change in enthalpy equals to the heat. Okay, so this portion is basically delta H of the system. We learned this from Gen Chem 1. Okay, enthalpy change in enthalpy equals the heat consumed or released by the system. Okay, so if we simply substitute Q for delta H, okay, we get this expression. So change in entropy of the surroundings equals to the the heat consumed or released by the system, or enthalpy change of the system divided by temperature. So let's bring this down. Copy. Okay, so let's say you are given change in entropy of a system. Okay, change in entropy of a system, and if you're given enthalpy of a system, can you find change in entropy of the universe? Although you were not given information about the change in entropy of the surroundings, you can still find the change in entropy of the universe using the previous equation that we've learned. Okay, so again, if we are given this value, and if we are given this value, we're able to find this value. Okay, so for example, in the sample exercise 19.5, the delta exercise 19.5, the the entropy change of the system of the reaction of producing ammonia is given as negative 198 kilojoule. If enthalpy change of the system of the reaction is given as negative 92 kilojoule, can you find the enthalpy change of the surroundings? Okay, so the answer is yes. We can definitely use this value to calculate the enthalpy change of the surroundings. Okay, one thing you have to note is that the heat released from the reaction is negative 92 kilojoule. Then how much heat is absorbed by the surrounding? Is it still negative 92? No, it's going to be positive 92. Whatever heat released by the system is absorbed by the surroundings. Okay, so now then the delta entropy of the surroundings is equal to positive 92 kilojoule, or divided by temperature 298. It was given as 298. Okay, and then if you have delta delta S of the surrounding, and if you have delta S of the system, you can easily calculate the delta S of the universe. Okay, so even if entropy change of the surroundings is not given, if we are given enthalpy change of the system, we can still calculate the total entropy change of the universe using this equation. Okay. So again, why do we care about entropy change of the universe? Why do we have to calculate this? Why is this so important? This is because positive and negative value of entropy of the universe will tell us whether a process is spontaneous or not. Okay, that's why calculating entropy of the universe is pretty important. Okay. Any entropy value larger than 0, any positive entropy value will tell us that whether a process is spontaneous or not. Okay. So as you can see from the previous slide, the spontaneity of the reaction seems to involve both enthalpy and entropy. Okay. Enthalpy delta H, entropy delta S. The spontaneity of the reactions involve both enthalpy and entropy. And American mathematician Willard Gibbs came up with a new state function called Gibbs energy or Gibbs free energy. Okay, Gibbs free energy or free energy. Okay, this is merely a derived quantity. Okay, this delta G is merely a derived quantity that blends together enthalpy and entropy. Okay, so if you multiply the entire equation that we just learned in the previous slide, this equation, okay, if we substitute this in here, this is the equation that we just learned. Okay, if we multiply the entire equation by temperature, T, and if we rearrange the positive and negative signs a little bit, you will get this, okay? You will get this expression, okay? This is just a rearrangement. And this is important. This portion is delta G, okay? I'm going to write that down here. Delta G is basically negative temperature, delta S universe. Okay. If you have a, if you are taking a note, um, uh, you can take a note. You do not have to pay too much attention how they arrived at this. Okay, how they arrived at this, how they arrived at this. Okay, you do not have to pay too much attention. Okay, it's very easy, very simple math rearrangement, but you do not have to pay too much attention. The only equation that you need to focus on is going to be this equation. Okay, so again, the Gibbs energy shows how enthalpy and entropy involves in determining the spontaneity of the reaction. So note that the enthalpy and entropy that we're using in this equation is all about the systems enthalpy and entropy. Okay, so the convenience about this delta G expression, okay, again, delta G is important because the delta S of the universe is important, right? It determines whether a reaction is spontaneous or not. Okay, so the convenience about delta G expression is that the surrounding portion is eliminated. Okay, so how you see surrounding portion here, that's eliminated. Okay, we can still evaluate the universe's entropy just by using systems enthalpy and entropy. Okay. So again, from in this slide, the two important things, delta G equation, in that the delta G is basically equal to negative T times entropy, change in entropy of the universe. Okay, so we've just learned that delta G is equal to enthalpy change minus temperature times entropy change. This is what we just learned. Okay, so and another thing that we learned is that delta G equals negative T delta S of the universe. Okay, so if a reaction is spontaneous, then if the reaction is spontaneous, then the left side of the equation is going to be negative. So then the delta G is going to be negative. So delta G is negative for spontaneous reaction. Okay. If a reaction is at equilibrium, there is no entropy change in the universe. There's no change in the entropy change of the universe. The oh, I'm sorry, I'm talking about the right side of the equation. Okay, then this portion is basically 0. Okay, then the delta G is going to be delta G is basically going to be 0. Okay, so the delta G is 0 for any system at equilibrium. If a reaction is spontaneous, okay, if a reaction is spontaneous, then for spontaneous reaction, we know that delta S is going to be positive, right? So the right side of the equation is going to be positive. Then delta G is going to be positive. So if delta G is positive, the reaction is uh, non-spontaneous. For I'm sorry. For non-spontaneous reaction, the delta S universe is going to be smaller than 0. Okay. Okay. Then because this is negative value, this side of the equation will be positive. Okay. So then delta G is going to be positive. Here, for spontaneous reaction, delta S of the universe is larger than 0. Okay. If it's larger than 0, this is going to be negative, and then the delta G is going to be negative. So just keep in mind that I'm going to summarize this. Delta G I'm going to summarize this here. Delta G smaller than 0, negative delta G, reaction is spontaneous. Delta G equals to 0, reaction is at equilibrium. If delta G is larger than 0, positive value, reaction is non-spontaneous. Okay, so again, to make a small note, for spontaneous reaction, delta S is positive, delta S of the universe, positive. Okay, for non-spontaneous reaction, delta S of the universe is negative. Okay, so this is what you have to memorize. Let's try a sample exercise. Calculate the standard free energy change for the formation of nitric oxide from nitrogen and oxygen at 298 Kelvin. Okay, given that enthalpy standard, okay, the knot here indicates the standard. Okay. Standard enthalpy change is 180.7 kilojoule and standard entropy change is 24.7 joule per Kelvin. Is the reaction spontaneous under these conditions? So in this question, we are asked to calculate the standard free energy change. What is standard and free energy change? Delta G naught. Standard, okay? Gives free energy, okay? So we're asked to find the standard free energy change for the formation of nitric oxide reaction. Since standard enthalpy and standard entropy values of the reaction of the system is given, okay, we just have to use the equation that we just learned in the previous slide to calculate the free energy. Okay. So delta G equals to delta H minus temperature delta S. Okay, this equation, it's not at standard state, but we are dealing with a standard situation. Okay, so we're going to convert this equation to delta G naught equals delta H naught minus temperature delta S naught. Okay, so we have all the necessary information. We just have to plug in the values. Okay, the enthalpy, the standard enthalpy change is 180 0.7 kilojoule minus temperature is 298 Kelvin. Okay, and then the entropy is in joule, so we want to convert joule into kilojoule. Since we know that kilojoule equal to 10 to the 3 joule, we can either have this ratio or this ratio. Okay, since we want to eliminate joule in the numerator, we want to multiply by this in order to delete the joule. Okay, so we're going to multiply by 1 kilojoule divided by 10 to the 3 power 3 joule. Okay, so then the joule's going to cancel. You're going to be left with kilojoule. So if we do all the math, we're going to have 173.3 kilojoule. Okay, so and what does this positive? You have positive value of Gibbs free energy. Okay, positive value of Gibbs free energy tells us that the reaction is non-spontaneous. Okay, so formation of nitric oxide at 2298 Kelvin, is this reaction spontaneous or not? The answer is no. Okay, the reaction is not spontaneous. Okay, let me know if anyone need more time for the previous slide. So, has anyone looked up the back of the textbook, Appendix C? Okay, so uh, if you have looked up the Appendix C, you must have noticed that Appendix C not only lists standard entropy values, but it also lists standard Gibbs free energy values too. So Appendix C lists all these values. Okay, the Gibbs free energy value listed in Appendix C, these values are pre-published. These are tabulated standard free energy formation labeled as delta GF. Okay, to write that down. Delta GF naught. This is standard free energy of formation. Okay, so if you want to calculate the standard Gibbs free energy change for a chemical reaction, you can also use the table in Appendix C. You can utilize the previously published value, okay? And then you can use this equation to find out the um, standard Gibbs free energy change for a chemical reaction. This equation is exactly the same as when we were finding the standard enthalpy change and standard entropy change of a reaction, okay? So the standard Gibbs free energy change for a reaction equals to the sum, okay, sum of the free energy of the product minus sum of the free energy of the reactants. Okay, and don't forget to multiply the stoichiometric coefficients or stoichiometric moles of products and reactants. Okay.
Professor, could you move up in the slide, please?
Uh-huh.
A little higher.
Here?
Yeah. Okay, thank you.
Let me know when you're done.
I'm done. Thank you.
Okay. And um, here are some notes regarding the standard free energy changes. If you are dealing with a reaction and it says the reactants and products are at standard state, okay, when you're dealing with a reaction and if the question says the reactants and products, the system is at standard state, that standard state indicates pure solid for any solid matter, pure liquid for any liquid matter, okay? 1 atmospheric pressure for any gases, okay? Concentration of 1 molar for any solution, and for any element mentioned as being in the standard state, the Gibbs free energy is going to be 0. Okay, so here are some notes regarding the standard states. Okay, try not to forget that. All right, let's try sample exercise. Use data from Appendix C, okay, to calculate the standard free energy change for this reaction, okay, at 298 Kelvin. Question B is asking what is the delta G naught, the standard state free energy change for the reverse reaction. Okay, so let's try A first. Okay, so this is just a simple exercise using already published standard Gibbs free energy values of the reactants and products to find the change in the standard free energy of an entire reaction. Okay, so again, okay, we're going to use the equation that we just learned to calculate the change in standard free energy of the reaction. Okay, and these free energy values of the reactants and products, they're listed in Appendix C, right? So delta G naught of the reaction equals to sum of the free energy of the uh, products minus sum of the free energy of the reactants. Okay, so as for the products, we have 4 moles of the phosphorus trichloride, the gas state, and minus, okay, this is the product, minus, as for the reactants, we have 1 mole of P4 gas. Plus 6 mole of the delta GF naught of the chlorine gas. Okay. So this is the product portion. This is the reactant portion. Okay, and then the values, these values you can find from the back of the Appendix C. Okay, if we plug in everything, we have 4 mole times negative 269.6 kilojoule per mole minus 1 mole times 24.4 kilojoule per mole. Okay, and then what's the value here? P4 gas state. That value is going to be 0. Okay, I'm sorry. Chlorine gas. Okay, so then the math turns out to be negative 1102.8 kilojoule. Okay, all the mole, they cancel out. You're left with kilojoule. Okay, so the standard free energy change for this reaction turns out to be a negative value. What does this tell us? This tells us that this negative value tells us that the negative values tell us that the reaction is spontaneous in the forward direction. Okay. Now, question B. Question B, it's asking to calculate the standard free energy change for the reverse reaction. Okay, what happens if you reverse this reaction? If you reverse this reaction, the reverse reaction, the math is basically going to be opposite. Okay, so we know that the delta G naught value is just going to be opposite of the forward reaction. So delta G naught of the reverse reaction is basically just going to be positive 1102.8 kilojoule. Opposite sign. Because you're doing opposite math. You're going to do the opposite math. So the positive value tells us that non-spontaneous in reverse direction. Okay, let's try another simple exercise. In section 5.7, we used Hess's law to calculate enthalpy change, standard enthalpy change for the combustion of propane gas at 298 Kelvin. Okay. Question A, without using data from Appendix C, predict whether delta G naught, the standard change in standard Gibbs energy for this reaction is more negative or less negative than the enthalpy change. Question B, use data from Appendix C to calculate the delta G naught for the reaction at 298 Kelvin. Is your prediction from part A correct? All right, so for question A, the question wants us to make a guess without performing any math. Okay, so since we already know that delta G naught equals delta H naught minus T temperature times delta S naught, we can make a guess about um, if we can make a guess about entropy change, we can definitely make a rough guess about the delta G value, right? Since entropy change, okay, this value is already given. So we only have to make a guess about this, and we will be able to make a guess about this. So entropy change here, entropy change. Entropy change is the change in order, measuring how much disorder a system becomes. So we need to take a look whether this reaction increases in entropy, or we need to make an evaluation whether this reaction increases in entropy or decreases in entropy. Okay, since the number of gas mole is reducing from 1 plus 5, you have 6 on the reactant side, and then you have 3 mole of gas in the product side. the number of mole of gas is reducing from 6 mole to 3 mole. This is reactant side and this is product side. The number of microstate is the number of microstate increasing or decreasing? Because you are decreasing the number of mole of gas, the microstate is decreasing. Okay, if the possible arrangement of atoms, possible arrangement is decreasing, number of microstate is decreasing, then what happens? Entropy also decreases. The delta S value is going to be negative. So if we plug in the negative delta S value here, negative delta S value, what happens to this portion? This entire portion is going to be positive. Okay, and if we are the enthalpy is given as negative 2220 kilojoule. If we are adding any value to negative 2220 kilojoule, delta G naught is going to be less negative, right? Where, okay, it doesn't matter how much you're adding. If you're adding something, if you're adding a positive value to this negative value, the delta G is going to be less negative. Okay, so we've answered our question for A. The question wanted us to make a guess, make a prediction whether delta G naught is going to be more negative or less negative than enthalpy. It is going to be less negative than the enthalpy change. Okay, so now we already made a guess. We're going to, for question B, we will actually use Appendix C, okay, where it lists standard free energy of formation to check and see if our guess is right or not. Okay. The change in Gibbs energy equals to, of the reaction equals to 3 mole times delta G naught of the carbon dioxide gas plus 4 mole of the delta G naught of the water in liquid form. This is the product. You minus all the reactants. You have 1 mole of delta G F naught of the propane plus 5 mole of the delta G F naught of the oxygen gas. Okay, so if we look up all of these values from the back of the book, Appendix C, we know that the standard Gibbs energy, the free energy change for carbon dioxide is negative 394.4 kilojoule per mole plus the standard free energy change for water in liquid form is negative 237.13 kilojoule per mole Okay, this is all the products minus 1 mole times standard free energy change of propane is negative 23.47 kilojoule per mole plus 5 mole, and the standard free energy change of oxygen gas is 0 kilojoule per mole. Okay, if we do all the math, we'll get negative 2108 kilojoule. And what can you tell about this value? Was our prediction right? Okay, compared to negative 2220 kilojoule, it actually became less negative. Okay, so our prediction was correct. Let me know if anyone needs more time for that slide.
I
Okay,
do.
you do?
Yeah. Sorry. Thank you. I'm done.
Okay. So, as we have just seen in the exercise that we just did, the delta G value, the free energy value of free energy value um, determines spontaneity of a reaction is dependent on enthalpy, entropy, and the temperature. Okay, so the delta G depends on enthalpy, entropy, and temperature. Okay, so we're going to take a look how signs of the enthalpy, entropy, and temperature affects the reaction spontaneity. How it affects the delta G. Okay, for example, if enthalpy and entropy have opposite signs, okay, it's rather simple. If enthalpy is negative and the entropy is positive, okay, if enthalpy is negative, entropy is positive, then this portion is going to be minus positive. Then your delta G is minus. Okay? Or minus minus uh, this is minus. Okay? Then the delta G is going to be minus. So in this situation where your enthalpy value is negative, entropy value is positive, delta G is going to be negative, and that indicates that the reaction is, or the system is going to be spontaneous at all temperatures. Okay. For example, let's take a look at a situation where enthalpy and entropy have same signs. Okay. Then what's going to happen is that the Gibbs energy is affected by the temperature. Okay. If the enthalpy is negative and entropy is negative, they both have same sign, then at low temperature, let's take a look at here. Okay, at low temperature, this is already minus. At low temperature, minus, if this is negative, this portion is going to be positive, right? At low temperature, minus plus small value is still negative. So then delta G is still negative, then that tells us that the reaction is going to be um, spontaneous. But when you have high value of temperature, high temperature, then if you minus plus a large value, then the delta G is going to be positive. Okay. Delta G is positive, and then the reaction is non-spontaneous. Okay, so it really depends on the magnitude of this T. Are you adding small value to this negative enthalpy, or are you adding large value to this negative enthalpy? Okay, so if you're adding a small value of to this enthalpy, the delta G is still going to be negative. If you're adding a small value to this negative, it's still going to be negative. If you're adding a large value to this negative enthalpy, then the delta G is going to be positive. Okay, so the magnitude of temperature becomes important when you have same sign for enthalpy and entropy. Okay, so this is what I've already discussed. Oh,
Can we go back like 2 slides to the most recent example you did? Just real quick.
oh, what's that again?
Can we go back like 2 slides to the most recent example you did? Like 1 slide before that.
This one?
There we go. Okay, I'm good. Thank you.
Okay. So let's try a sample exercise where delta G is affected by temperature. Okay, the Haber process for the production of ammonia. Okay, we've encountered Haber process many times in this course. Haber process for the production of ammonia involves equilibrium. Okay, for this reaction, the enthalpy change, the standard enthalpy change is negative value, and the standard entropy change is also negative value. Enthalpy and entropy both have negative, both have same sign. Okay, this case. Assume that standard enthalpy change and standard entropy change for this reaction do not change with temperature. A, predict the direction in which delta G for the reaction changes with increasing temperature. Okay. B, calculate delta G at 25 degrees Celsius versus 500 degrees Celsius. So for question A, okay, okay, if we're given that both enthalpy and entropy values have same sign, both negative, we know immediately that this will be affected, the delta G of this reaction will be affected by the reaction temperature, right? It will be affected by the reaction temperature. Okay, how will this affect? We're going to discuss that. So the situation given here is that increasing temperature. Increasing temperature. Okay, so we need to evaluate a situation. We need to find out what's going to happen to this Gibbs free energy with increasing of the temperature. If the temperature increases, this portion is going to be large. Okay, as temperature increases, you're multiplying large value to this delta S, you're going to have large value. Okay, so then however, the delta S is negative, so you have you are basically adding large value to the enthalpy. Okay, so then minus the enthalpy value is minus, right? Negative value. if you are adding large value to this negative enthalpy, what's going to happen to the delta G? If you're adding a large value to this negative enthalpy value, the delta G is going to be positive. Why? Because you're adding a large value to the enthalpy. Okay, not positive. Positive is inaccurate. So delta G will increase with temperature increase. Okay, why? You're adding large value to this negative enthalpy value. Okay, so what does this tell us? This tells us that if delta G becomes more and more positive as temperature increases, this tells us that the reaction is becoming more and more non-spontaneous as temperature increases. What does that mean? What does it mean by not becoming more and more non-spontaneous? This means it will produce, it doesn't mean it will produce more or less ammonia. This means it will produce less ammonia. Okay, the delta G, the reaction is going to be less and less non-spontaneous as temperature increases. That means the reaction will produce less and less ammonia as the temperature increases. As temperature increases. Becoming non-spontaneous, more and more non-spontaneous as temperature increases. Let's do some actual math to calculate the comparison between delta G of the reaction at low temperature versus high temperature. See if our prediction is right or not, okay? So at 25 degrees Celsius, we need to have everything in Kelvin, okay? So 25 degrees Celsius is basically 289 Kelvin. 500 degrees Celsius is basically 77.3 Kelvin. Okay, so at 298 Kelvin, the change in standard free energy is going to be enthalpy negative 92.38 kilojoule minus, okay, minus temperature is 298 Kelvin times entropy value, negative 198.3 joule per Kelvin. Again, this is in joule, this is in kilojoule. We need to make a conversion. We know that kilojoule equals 10 to the 3 joule. We can use either expression, okay? In order to eliminate joule, we're going to use this expression. Okay, so multiply by 1 kilojoule divided by 10 to the 3 joule. The joule and joule will cancel out. Okay. And then if we do all the math, we get negative 3 33.3 kilojoule. Okay. Let's calculate the delta G at higher temperature. Okay, at 77.3 Kelvin, delta G is equals to enthalpy minus temperature times entropy okay, this equals to 61 kilojoule. Okay, so as we predicted, okay, as temperature increases from 298 Kelvin to 773 Kelvin, what happened to the delta G? The delta G value increased. Okay, the delta G value became more and more positive as temperature increases. This tells us that this confirmed, okay, our prediction in A. Okay. All right. So far we have focused on looking at the reactions at standard states, right? So the delta G naught is the standard state. Standard state gives free energy change. Standard state. So far, we've focused on looking at reactions at standard state, 1 atmospheric pressure, 1 molar, pure liquid, pure solid. Those are the standard states. However, in reality, most chemical reactions actually occur under non-standard conditions. So therefore, chemists came up with another equation to find the Gibbs free energy at non-standard situations. Okay. And the convenience, and they came up with this equation. The convenience of this equation is that you can find Gibbs free energy change at non-standard conditions from the standard condition. Okay, so you can use standard conditions Gibbs free energy to find the Gibbs free energy at non-standard conditions. Okay, you can find non-standard free energy from standard free energy. Okay, it's given by this equation. The equation, the R is the ideal gas constant. Okay, R is the ideal gas constant, 8.314 joule per mole Kelvin. Okay, T is the temperature, gas constant, temperature. What is the Q? Q is the reaction quotient. Quotient. What is the reaction quotient? We've learned this in chapter 15, chemical equilibrium. Reaction quotient is basically product concentration divided by reactant concentration, right? Each raised to the power equivalent to the coefficients in the balanced stoichiometric balance equation. So you have two different types of Q. You have QC and QP. Okay. Some of you guys might already have forgot what we discussed in chapter 15, but QC is the reaction quotient using product and reactant concentrations. Okay. P here is the partial pressure. Okay, so QP is going to be product partial pressure divided by reactant partial pressure. QC is the product concentration divided by reactant concentration. Okay, again, don't forget to raise the power equal to the coefficients. Okay, so if you forgot about the reaction quotient Q, please revisit chapter 15. So the Gibbs free energy at non-standard state can be found from this equation. You use the standard state free energy plus this portion. Okay, the ideal gas constant times temperature times natural log of reaction quotient Q. Okay, so at standard condition, we've already learned that the concentration will be 1 molar, right? Concentration is 1 molar. This is true for both products and reactants. So if the ratio of product and reactants is 1, the reaction quotient is 1. Okay, natural log of 1 is going to be 0. So this later portion drops out at standard state. Therefore, what's going to be left over? At standard state, delta G equals to delta G naught. Okay, so again, a standard condition Gibbs free energy is basically delta G naught. Non-standard condition, you have to use this equation to find the Gibbs free energy at non-standard system. Let's try a sample exercise. Write a chemical equation that defines a normal. Actually, okay, I'm actually going to skip this. So can you guys please cross this out? Okay, this is a sample exercise related to what we just learned. I'm going to bring the equation down. Copy. Okay, I'm going to read the question. Calculate delta G, non-standard Gibbs free energy, at 298 Kelvin for a mixture of 1 atm nitrogen, 3 atm hydrogen, and 0.5 atm ammonia being used in Haber process. And please add a note. The delta G naught, the standard Gibbs free energy for this process already previously been calculated to be negative 33.3 kilojoule. Okay. All right, so now we have all the information we need. We just have to do some math to find the delta G at non-standard state. Okay. Before we do anything, let's find the reaction quotient Q. Okay. So reaction quotient Q here is not just regular Q. You need to have proper label. It's QP. Okay, reaction quotient using partial pressure. Okay, so the if you forgot about the reaction quotient, please revisit chapter 15. Okay, the equation for reaction quotient QP is going to be partial pressure of product raised to the power equivalent to the coefficient, which is 2, divided by partial pressure of the first reactant raised to the power equivalent to the coefficient, power 1, times partial pressure of the second reactant, hydrogen, okay, raised to the power equivalent to the coefficient, raised to power 3. Okay, the partial pressures are already given. We just have to plug in. So 0.5 squared divided by 1 raised to the power 1 times 3.0 raised to the power 3. That equals to 9.3 times 10 to the negative 3. Now that we have Q value, we know the gas constant, we know the temperature, we can now finally find the Gibbs energy at non-standard state. Okay, so delta G is equals to delta G naught delta G is negative 33.3 kilojoule plus gas constant is 8.314 joule per mole Kelvin. Again, you have joule, so we're going to multiply by 1 kilojoule over 10 to the power of 3 joule so that we can convert the joule into kilojoule. Okay, and then the temperature, we have 298 Kelvin. We have it in Kelvin, so that's nice. And then natural log of 9.3 times 10 to the negative 3. If we do all the math, we have negative 44.9 kilojoule per mole. Okay, so we have now successfully found the Gibbs free energy at non-standard state using the standard state free energy. Okay, so the previous sample exercise that we dealt with, this was an equilibrium reaction. This Haber process, this is equilibrium reaction. This is an equilibrium reaction. But was the reaction condition made the reaction be at equilibrium? This equilibrium reaction always has to be at equilibrium? No, the equilibrium reaction, although it is an equilibrium reaction, the equilibrium can be shifted. Okay, if you can recall from chapter 15, we need to compare the reaction quotient Q value to the K value. If the reaction quotient value for Haber, this quotient value of the Haber process, we just found to be, this is a Q value, 9.3 times 10 to the negative 3. If this quotient Q value equals to the equilibrium constant value, then we know that the reaction is at equilibrium. If the Q value doesn't equal K value, then we know that the reaction is not at equilibrium. The equilibrium is shifted due to the change of the pressure, change of the temperature, adding reactant, removing the product, all those factors, okay, Le Chatelier's principle, right? All those factors can shift the equilibrium, okay? So when Q value doesn't equal K, reaction is not at equilibrium. Okay. All right, so let's say the reaction is at equilibrium. Then we know two things. At equilibrium, the first thing we know is that Q equals K. Okay, reaction quotient equals to the equilibrium constant at equilibrium. Delta G is equal to 0 at equilibrium. Okay, again, we discussed in the slide 33. Slide 33 up there. I don't want to go back to the previous slide. It's going to freeze the screen, but we discussed in the beginning of this lecture. Okay, so at equilibrium, we know these two things. Then the reaction explaining relationship between delta G and delta G at non-standard state and standard state. This equation will become this. Delta G is 0. Okay, so this whole portion equals to 0 at equilibrium. Okay, so if you rearrange a little bit, if you do some rearrangement, you will get this. Okay, again, you don't really have to know how we rearranged it. You just have to know this. Okay, if you have time, you can take out a piece of paper and use your pen. Do the rearrangement. It's pretty simple, but the rearrangement part is not the focus here. The focus here is that we arrive at this expression. So this equation, why is it useful? Because we are able to calculate the equilibrium constant if we know the value of the standard state Gibbs energy. Okay. we can calculate equilibrium constant K if we know standard Gibbs free energy value. Let's try a sample exercise. Okay, the standard free energy change. The standard free energy change for Haber process at 25 degrees Celsius was obtained in sample exercise 19.9. Okay, we have already calculated this. Okay, in sample exercise 19.9. Use this value delta G naught to calculate the equilibrium constant for the process at 25 degrees Celsius. Okay. So in this question, the expression that we just learned is K equals E to the negative delta G naught divided by RT. Okay. So in this question, delta G is given, temperature is given, so and the gas constant we already know. So we can simply use this equation to calculate the equilibrium constant for the Haber process. Okay. 25 degrees Celsius is going to be 298 Kelvin. Okay. So using the let's plug in all the values. K equals E to the negative 33300 joule per mole divided by gas constant is 8.314 joule per mole Kelvin. Actually, I'm going to magnify this. K equals E to the negative 33300 joule per mole divided by gas constant is 8.314 joule per mole Kelvin times 298 Kelvin.
Professor,
Uh-huh.
isn't there supposed to be a negative sign next to the 33,300?
Oh yeah, my bad. Here. Everything good?
Yeah.
Okay. So joule per mole cancel, Kelvin cancels. You don't have any unit anymore. So K equals to E to the power of, if you do all the math, you will get 13.4. That equals to 7 times 10 to the 5. All right. Before we finish off, let's just try to compare the Q value from sample exercise 19.11. Let's compare this Q value versus the K value. Okay, so the Q value here, the Q value from the Q value was 9.3 times 10 to the negative 3. So compare Q versus K. Okay, the Q value is 9.3 times 10 to the negative 3. Does it equal to K value? It doesn't, right? So the reaction condition from that exercise 19.11 tells us that under that condition, the Haber process is not at equilibrium. Okay, the Q value, this value is actually smaller than K. What does Q smaller than K indicates? Again, if you forgot, revisit chapter 15. This tells us that the reaction shift to right. Okay. Okay. And again, if Q value equals K, the reaction will be at perfect equilibrium. All right, I'm going to end the lecture here. I'm going to hang around for another 5 to 10 minutes just in case anybody else has questions.